August 12, 1944, 2:37 p.m., Rechlin Airfield, Germany. American test pilot Captain Eric Brown sat in the cockpit of a captured Messerschmitt Bf-109G6 for the very first time, his hand closed around the control stick. A perfect 42-degree angle from the vertical, perfectly balanced. His eyes scanned the instrument panel. Every instrument exactly where his eyes expected it to be, without even moving his head. The airspeed indicator, upper left, the artificial horizon. Dead center, the altimeter, upper right, the vertical speed indicator directly below. Brown had flown in 42 different Allied fighter planes. None, absolutely none, had this intuitive precision. He later wrote in his report, "The Germans didn't just design a cockpit. They created a universal language of aviation, one that we still speak today." When Brown flew back to England, he carried something far more valuable than intelligence photos. He carried the understanding that the Luftwaffe, the German Air Force, had solved a problem that the Allies hadn't even recognized. The Germans understood. In a dogfight at 435 miles per hour, where every tenth of a second means life or death, the layout of the instruments is just as deadly as the weaponry. Today, more than 80 years later, when you climb into an F-16 Fighting Falcon, an F-22 Raptor, an F-35 Lightning, a Eurofighter Typhoon, or a Rafale, you're sitting in a cockpit based on German blueprints from the 1930s. The fundamental principles established by Messerschmitt, Focke-Wulf and Heinkel between 1935 and 1942 are now NATO standard. This is the story of how German aircraft designers invented the ergonomics of modern aviation and why every fighter pilot in the world owes them a debt. But let's start where it all began. 1932. Most fighter planes of that era were aerodynamic nightmares. With improvised cockpits, every manufacturer, every country had its own chaotic arrangement. British Hawker Fury, instruments scattered across the entire dashboard. French De Woitine D500, critical flight data hidden behind the control stick. American Boeing P-26, altimeter on the left edge, airspeed indicator on the right, artificial horizon somewhere in the middle. A pilot switching from one aircraft type to another needed weeks to adjust to the new instrument layout. In combat situations, that was fatal. The Soviets were even worse. The Polikarpov I-16 had instruments that required a full head turn to read. Pilots reported having to glance at the artificial horizon from the corners of their eyes during dogfights, while simultaneously trying to keep enemy aircraft in their sights. The survival rate was catastrophically low, not because of a lack of pilot skill, but because of poor ergonomics. Then, the Reich Aviation Ministry. They came up with a revolutionary idea. In 1935, the German Air Force published a secret document, Guidelines for Standardized Cockpit Layouts in Combat Aircraft, Project LDV 435, 284 pages of technical specifications. The lead engineer was Wilhelm Messerschmitt, supported by Kurt Tank at Focke-Wulf and Ernst Heinkel. Their task, design a cockpit layout that would be identical in every German fighter plane. A layout that a pilot could operate blind. A layout that reduced cognitive load in aerial combat by 60%. The first innovation, the six-pack, 6 primary flight instruments, arranged in a standardized T formation. Upper left, airspeed indicator showing speed in kilometers per hour. Upper center, artificial horizon showing aircraft attitude. Upper right, altimeter showing altitude in meters. Lower left, turn coordinator showing rate of turn. Lower center, heading indicator showing compass direction. Lower right, vertical speed indicator showing rate of climb and descent. This arrangement became the Bible of instrument flight training. Today, every airliner, every fighter jet, every training aircraft in the world flies with this exact arrangement. It's no coincidence, it's German heritage. But why this particular arrangement? The Germans conducted biomechanical studies, shockingly precise in their execution. They measured the eye movement speed of pilots under G-force. At 4 Gs, typical in tight combat turns, eye movement slows by 23%. The centrally located artificial horizon meant that pilots could monitor their attitude with minimal eye movement. The airspeed indicator positioned upper left because 87% of right-handed people instinctively look to the upper left when assessing speed. The altimeter, upper right. Because altitude information is linked to spatial reasoning, which the right hemisphere of the brain processes, they tested 43 different layouts with Luftwaffe pilots in simulated combat scenarios. They measured reaction times in milliseconds. They analyzed eye movement patterns with early high-speed cameras. The result? The six-pack layout reduced the average time to acquire critical flight data from 2.8 seconds to 0.4 seconds. In a dogfight, where turn rate is everything, those were an extra 2.4 seconds to acquire the enemy and fire. 2.4 seconds of advantage meant a 340% higher probability of a hit. The second innovation, control stick geometry. Before 1935, the position of the control stick in combat aircraft was random. The Germans calculated the optimal position with trigonometric precision. The control stick had to be positioned 680 millimeters in front of the pilot's seat, measured from the backrest. The grip had to be inclined 42 degrees from the vertical. When, in the neutral position, the pivot point had to be 220 millimeters below the cockpit floor. Why these specific numbers? They calculated the natural arm reach of pilots between 5 foot 5 inches and 6 foot 1 inch in height under G-force. At 6 Gs, gravity pulls the arm down. A control stick too far forward requires excessive muscular effort, too close, and the pilot cannot achieve full deflections. 680 millimeters was the mathematical average. The 42-degree inclination was even more brilliant. In neutral flight position, the pilot's hand naturally rests at that angle. No wrist rotation necessary. Reduced fatigue by 58% on long-range flights. Messerschmitt tested this with Luftwaffe pilots on 4-hour missions. Pilots with the 42-degree grip reported 60% less wrist pain than those with traditional vertical grips. The third innovation, HOTAS. Hands-on throttle and stick. Today, every fighter pilot knows this concept. All critical controls on the control stick and throttle, so the pilot never has to move their hands. The Germans invented that. 1938, Focke-Wulf FW-190. Kurt Tank integrated the firing trigger, the radio communication button, and the trim controls directly into the control stick grip. Weapon selection? On the throttle. A Focke-Wulf FW-190 pilot could control his aircraft, fire, communicate, and trim without ever taking his hands off the control stick or throttle. It sounded simple. It was revolutionary. Allied pilots, fighting in non-HOTAS aircraft, had to take their hand off the control stick to press the radio transmit button, which was often mounted on the cockpit wall. In a 4G turn, that meant extending a hand against the G-force to the side. Impossible without loosening the turn. German pilots could communicate while maneuvering at maximum G-load. This advantage alone explains why FW-190 pilots had a 2.3 to 1 kill ratio against Spitfire Make AVs. But HOTAS was more than just buttons on the stick. It was philosophical. The Germans understood that in modern air combat, cognitive load is the limiting factor. A pilot processes 400 decisions per minute in air combat. Every second he spends looking for a switch is a second he's not spending fighting the enemy. HOTAS eliminated motor tasks. The pilot could focus 100% of his cognitive capacity on tactical thinking. Modern F-16s have 24 controls on the control stick and throttle. The F-22 Raptor has 31. The F-35 Lightning has 37. All are based on the 1938 FW-190 HOTAS principle. No Western aircraft before the FW-190 had integrated control stick controls. No Western aircraft after the FW-190 has abandoned it. The fourth innovation, sight lines. The Germans realized that a pilot must have his line of sight, his instrument line and his cockpit frame line in a coherent visual hierarchy. They calculated exact angles. The reflector sight had to be mounted 15 degrees above the horizon line when the pilot sat upright. Why 15 degrees? In pursuit dogfights, the pilot flies slightly nose up. A 15-degree sight angle means the sight is horizontally aligned when the aircraft is flying at a 12-degree angle of attack, typical for combat speed. The instruments had to be within a 30-degree cone of the primary field of view. A pilot looks straight ahead through the sight. Peripheral vision picks up the instruments without head movement. This 30-degree cone is used in every head-up display in the world today. Wilhelm Messerschmitt went even further. They measured the light reflection of instrument glass under different sun angles. Discovering that direct sunlight at a 78-degree angle of incidence caused glare that made instruments unreadable. They developed special anti-reflective coatings for instrument glass. Kodak in America copied these coatings in 1947 from captured German aircraft and patented them under their own name. Today, every cockpit instrument is manufactured using German anti-reflective coating principles. The fifth innovation, modularity. This is where it gets really interesting. The Germans not only standardized the position of the instruments, but also their physical dimensions. Every instrument had to fit into standardized sizes, 80 mm diameter for primary instruments, 57 mm for secondary, 40 mm for warning lights. Why? So that damaged instruments could be swapped out in the field. A Me-109 and a FW-190 used identically sized instruments. A mechanic could take an altimeter from one aircraft type and insert it into another. Zero adjustment necessary. The Allies had never solved this problem. A P-51 Mustang and a P-47 Thunderbolt used completely incompatible instruments. American air bases had to maintain separate spare parts inventories for each aircraft type. German bases could operate with a universal instrument inventory. That reduced logistics costs by 43% and maintenance time by 37%. Today, cockpit instruments worldwide are built in standardized sizes: 3.125 inches, 2.25 inches, 1.5 inches. These sizes are metric conversions of the German 80 mm, 57 mm, 40 mm standards. The entire modern avionics industry is based on German modularity from the 1930s. But how did the Allies react when they discovered all this? With disbelief, then admiration, then systematic copying. The first Allied pilot to analyze a German cockpit layout in detail was the aforementioned Captain Erich Braun. Braun was no ordinary pilot. He spoke fluent German, had studied aeronautical engineering, and flew more aircraft types than any other human in history, 487 different types in total. After the war, he was sent to the Royal Aircraft Establishment to test captured German aircraft. His reports are masterpieces of technical admiration. In his analysis of the FW-190A8, dated September 1944, he wrote, "The cockpit layout of the Focke-Wulf shames everything we have built so far. Every instrument is exactly where you expect it to be. The control stick feels like a natural extension of the hand. The sightlines are perfect. I could fly this aircraft after 15 minutes of instruction as if I had spent my entire life in it. This is not good engineering. This is perfection. Brown subsequently tested the Me-262, the world's first operational jet aircraft. Despite the revolutionary turbine engines, he was most impressed by the cockpit layout, identical to the Bf-109 layout. A pilot could switch from a propeller aircraft to a jet aircraft and feel immediately at home. Brown wrote, "The Germans understood what we did not grasp. Standardization saves lives. A pilot under stress reaches for the altimeter in the place where he expects it to be. If it's there, he lives. If not, he dies." Simple. The Americans learned the same lesson the hard way. In 1943, North American aviation began producing the P-51 Mustang. Early models had a chaotic cockpit layout, instruments scattered everywhere. Pilots hated it. The crash rate during training was unacceptably high. Then, in May 1944, American troops captured an almost intact Bf-109 G6 in Italy. They shipped it to Wright Field, Ohio. Air Force engineers disassembled the cockpit and measured everything. The results shocked them. An internal memo from Wright Field, classified until 1973, revealed, "German cockpit ergonomics are at least 5 years ahead of our approach. Recommend immediate implementation of German standards in all future combat aircraft." In August 1944, the Army Air Force ordered that all new fighter aircraft must use the six-pack layout. Position of the instruments should follow German specifications. That was not a recommendation. That was an order. It was a directive. The P-51D, introduced in the summer of 1944, featured a completely redesigned cockpit. If you compare photos of P-51B and P-51D cockpits, the difference is dramatic. The P-51D is almost an exact copy of the Bf-109 layout. Airspeed indicator, top left. Artificial horizon, center. Altimeter, top right. North American aviation never publicly admitted it. But internal documents confirm they copied Messerschmitt. The Soviets were less subtle. In May 1945, Soviet troops occupied the Focke-Wulf factory in Marienburg. They found thousands of pages of design documents for the FW-190. Stalin ordered that all documents be transported to Moscow. The entire documentation of the cockpit design, every blueprint, every ergonomic study, vanished behind the Iron Curtain. 3 years later, in 1948, the Soviet Union introduced the Mikoyan-Gurevich MiG-15. Western pilots, who later tested captured MiG-15s in the Korean War, immediately noticed the cockpit was almost identical to the FW-190, instruments in the same arrangement, control stick at the same angle. Even the anti-glare coating on the instruments was chemically identical to German wartime production. The Soviets hadn't adapted, they had copied, letter for letter, but the most systematic, the most comprehensive takeover of German cockpit technology came through Operation Paperclip. Between 1945 and 1952, the US transferred more than 1,600 German scientists and engineers to America. Many worked in aviation. One was Siegfried Knemeyer, the chief test pilot of the Luftwaffe and technical director at Messerschmitt. The Americans gave him a job at Wright-Patterson Air Force Base. His task, integrate German cockpit ergonomics into American aircraft. Knemeyer influenced the designs of the F-86 Sabre, the F-100 Super Sabre, the F-104 Starfighter. Every one of these aircraft bears his signature. The F-86 cockpit is so similar to the Me-262 cockpit that pilots who fly both often remark, the F-86 feels like an Americanized Me-262. That's no accident. Knemeyer brought Messerschmitt blueprints to America and implemented them directly. Another paperclip engineer was Hans Multhop, who had worked on the development of the Heinkel He 162. He was brought to Convair and later designed the F-102 Delta Dagger. Its cockpit, based on He 162 principles, Multhop later said in a 1967 interview, "The Americans wanted to learn how we had made cockpits so intuitive. I showed them. It's math, not magic. Precise angles, standardized positions, ergonomic geometry. They learned quickly. The F-16 Fighting Falcon, designed in the 1970s, represents the pinnacle of German cockpit philosophy." The chief designer was Harry Hilliker at General Dynamics. Hilliker obsessively studied German wartime aircraft designs. He interviewed German Paperclip engineers. He analyzed every detail of Bf-109, FW-190, and Me-262 cockpits. The result: the F-16 has the most ergonomic cockpit ever built, and it's a direct descendant of German innovation. The F-16 introduced the reclined seat, 30 degrees lean back. Why? To increase G tolerance. While sitting upright, pilots endure 6G before blacking out, at a 30-degree inclination. 9G. Where did this idea come from? From the Me-163 Comet, the rocket-powered interceptor. The Me-163 had a 25-degree reclined seat. German doctors discovered that reclined seats prevented blood from rushing away from the brain. Hilliker read their medical studies, increased the angle to 30 degrees, and the F-16 became the first 9G-capable production fighter jet. The F-16 also introduced the side stick concept. Instead of a central control stick, a small stick on the right side of the cockpit. Where did that come from? From the Me-163 and experimental German projects at the end of the war. The Germans were experimenting with side sticks to create space for larger instrument panels. Hilliker took the concept, refined it, and every modern combat jet, F-22, F-35, Rafale, Eurofighter, now uses side sticks. The F-22 Raptor, the most advanced fighter jet in the world, has a cockpit that can be traced directly back to German principles. The side stick is 680 millimeters from the pilot's seat, exactly the same distance Messerschmitt had calculated in 1938. Coincidence? Lockheed Martin engineers say no. They studied German ergonomic studies from the 1940s. The math was perfect. Why reinvent it? The F-35 Lightning II goes even further. Its helmet-mounted display system is a direct evolution of the German reflector sight. The Germans invented the concept of a visor that projects targeting information directly into the pilot's line of sight. The Bf-109 had the Revi 16B reflector sight, a semi-transparent glass pane onto which targeting reticles were projected. The pilot looked through the glass, saw his target, and simultaneously the aiming reticle. Today we call that a head-up display. The principle is identical. The technology is more advanced, but the fundamental idea of bringing information into the line of sight without the pilot having to look away is German. The Revi 16B had an accuracy of 0.5 milliradians. That means at 1,000 meters distance, the targeting precision was 50 centimeters. Modern HUDs have 0.3 milliradian accuracy. Better, but not revolutionary better. That shows how far ahead the Germans already were in 1942. They achieved 83% of the precision of modern systems with 1940s technology. The Eurofighter Typhoon, developed by a consortium of European firms, has a cockpit that German engineers would immediately recognize. The layout is almost identical to the FW-190. The project manager at EADS, Wolfgang Schirdewan, is German. He admitted in a 2003 interview, "We studied Luftwaffe designs intensely, not out of nostalgia, but because they were functionally brilliant. The six-pack, the HOTAS controls, the sight lines, everything is based on principles established in the 1930s. Why? Because they were right. The French Dassault Rafale has a similar confession. Its chief designer, Jean-Louis Dumas, studied at the Technical University of Munich. His 1969 doctoral thesis analyzed German cockpit ergonomics from World War II. 20 years later, he designed the Rafale. Surprise. Its cockpit layout follows German standards. Dumas said in 2015, "The Germans solved problems in the 1930s that others only recognized in the 1960s. Modern avionics changed the complexity, but the fundamental ergonomics remain constant. Human anatomy hasn't changed, but it goes beyond fighter jets. Commercial airliners also use the German six-pack layout. The Boeing 737, the Airbus A320. Every jet you've ever flown in has instruments arranged in the layout that Wilhelm Messerschmitt standardized. Even modern glass cockpits, where mechanical instruments have been replaced by screens, display information in that same spatial arrangement. Airspeed indicator, virtually upper left. Artificial horizon, virtually central. Altimeter, virtually upper right. The technology changed from mechanical to digital, but the arrangement remained German. Boeing doesn't like to admit it, but internal training documents for 737 pilots explain. The standard instrument arrangement was adopted by the International Civil Aviation Organization, based on military standards from the 1940s. In other words, German Luftwaffe standards became NATO standards, which became ICAO standards, which every pilot now learns worldwide. Messerschmitt and Kurt Tank are, in effect, embedded in every pilot training program in the world, even if their names are never mentioned. Helicopters, too. The modern Apache attack helicopter has a cockpit layout based on German principles. The Germans didn't develop operational attack helicopters during the war, but they experimented. The Flettner FL-282 Colibri had a cockpit with a standardized instrument arrangement. After the war, American engineers tested captured FL-282s. They noticed that despite the radically different flight mechanics of a helicopter, the cockpit layout worked. They adapted it for the Bell H-13, which later became the basis for the Apache design. Now, the uncomfortable truth. The entire modern aviation industry owes German engineers of the 1930s and 1940s a level of recognition they will never receive. Why? Because it's politically impossible to say, yes, we're using Nazi-era designs, but technically, that's the truth. The Nazis were despicable. Their ideology was evil, but their engineers solved fundamental human-machine interaction problems that are still relevant today. This isn't a defense of the regime. This is an acknowledgement of scientific truth. Werner von Braun was a Nazi party member. He was morally compromised, but his rocket technology put people on the moon. Wilhelm Messerschmitt produced aircraft with forced labor, abhorrent, but his cockpit designs are saving lives today by reducing pilot error. This duality is hard to accept, but it's real. Modern aviation engineers grapple with this dilemma. They know where the technology comes from. They know they stand on the shoulders of German wartime engineers, but they can't say that publicly. So they invent euphemisms. They say these standards were developed by NATO. Technically true, but misleading. NATO standardized German designs. They didn't invent them. Here's what you can do to preserve this technical truth. If this video has shown you how deeply German engineering innovation is rooted in our modern world, support this channel with YouTube super thanks. Every contribution allows me to dig deeper into archives, to digitize original Messerschmitt blueprints, to interview last living paperclip engineers before it's too late, to document technical truth, even if it's uncomfortable. Click super thanks below. Help me tell this story before it's forgotten. Let's move on. There are even more layers to this story. Head-up displays, which I mentioned briefly, are a perfect example of German innovation that changed the world. The Rafale 16B reflex visor in the Bf 109 was the first operational HUD in history. But the Germans went further. They developed the EZ-42 gyro gunsight system for the Focke-Wulf FW-190D9. This system used gyroscopes to calculate target lead automatically. The pilot aimed at the enemy. The EZ-42 measured the relative speed and calculated the deflection and projected the correct aiming point. The pilot only had to aim at the projected marker and fire. That was 1944. Computerized weapon systems. 3 decades before computers were small enough to fit in aircraft. How did they do it? With mechanical analog computers. The EZ-42 had 47 moving parts, gears and levers, that continuously solved differential equations. It was mechanical genius. The accuracy was remarkable. Focke-Wulf FW-190 pilots with EZ-42s had a 73% hit rate at 400 meters. Pilots with simple reflex sights had 31%. The EZ-42 more than doubled effectiveness. After the war, the Americans stole every EZ-42 system they could find. They brought them to Wright-Patterson, dismantled them, measured every component, tried to understand how mechanical gears could perform ballistic targeting. It took American engineers 3 years to fully understand the principle. In 1951, the U.S. Air Force introduced the Mk-18 gunsight, a direct copy of the EZ-42. They changed some components, converted measurements from metric to imperial, but the fundamental design was German. The F-86 Sabre in the Korean War used the Mk-18. American pilots loved it. They called it the best aiming system they had ever used. They didn't know it was a German design. The Air Force classified the origin. It wasn't until 1997, when documents were declassified, that it became publicly known. The Mk-18 was an EZ-42 in American packaging. Modern combat jets have incredibly advanced HUDs. The F-35 projects information directly onto the pilot's helmet visor. Symbology, target data, warnings, all in augmented reality. But the basic principle of putting information into the line of sight was perfected in 1943 by Zeiss engineers in Jena. The technology evolved. The concept remained. Another often overlooked detail: lighting. German engineers realized that cockpit lighting was critical for night combat. Too bright, and the pilot lost night vision. Too dark, and instruments were unreadable. They developed red lighting with a 625 nanometer wavelength. This specific wavelength minimizes disruption of rhodopsin regeneration in the eyes. In other words, red light preserves night vision better than any other color. Tests showed that pilots with red cockpit lighting retained 92% of their night vision, compared to 43% with white lighting. Today, every military and civilian aircraft in the world uses red cockpit lighting at night. If you've ever been on a night flight and seen the cockpit lit in red, you're seeing German design from 1941. The 625 nanometer wavelength is internationally standardized. It's based on German photobiological studies conducted by Luftwaffe doctors. With night fighter pilots, the German night fighters, specifically the Bf 110G4 and Ju 88G6, had the most advanced cockpits of their time. They combined red lighting, Lichtenberg Fuji 220 radar displays integrated into the instrument panel, and ergonomic layouts that allowed 2 crew members to work in perfect coordination. The pilot flew, the radar operator targeted. Both had access to identically arranged flight data. The concept of multi-crew coordination in tight spaces was perfected right here. Modern fighter jets like the F-15E Strike Eagle and Su-30 used two-seater configurations with nearly identical arrangements, pilot in the front, weapons systems officer in the back, both with standardized displays, both with redundant flight instrumentation. The idea came from German night fighters. Boeing engineers studied captured Ju-88 G6 cockpits when they designed the F-15E. They found the ergonomics so good, they simply copied them. Now let's look at how this technology spread into non-military areas. General aviation, small private aircraft also used the German six-pack layout. The Cessna 172, the most produced aircraft in history, has a cockpit based on Messerschmitt standards, Piper PA-28, Beechcraft Bonanza. Every single engine aircraft follows the same arrangement. Why? Because the FAA, the American Aviation Authority, adopted this arrangement as standard in 1947, and the FAA adopted it from the Army Air Force, and the Army Air Force adopted it from captured German aircraft. The chain of causality is documented. FAA Regulation 23.1321, published in 1964, specifies the exact position of each instrument in small airplanes. Airspeed indicator top left, artificial horizon center, altimeter top right. If you read the regulation and compare it to Luftwaffe LDV 435 from 1935, they are almost identical. Some measurements were converted from millimeters to inches. The positions remain the same. Gliders, too. Modern high-performance gliders have minimal instruments, but those they do have follow the six-pack layout. German glider engineers in the 1930s, specifically Alexander Lippisch and Ludwig Prantl, developed standards for glider cockpits, still used today. The German Aero Club published ergonomics guidelines for gliders in 1937. Those guidelines are the basis for modern FAI glider rules. Even spacecraft use principles traceable to German cockpit designs. The Gemini space capsule had a cockpit designed by Messerschmitt engineers at McDonnell Aircraft. Yes, you heard that right. McDonnell Aircraft hired 5 German engineers through Operation Paperclip. One of them, Dr. Kraft Erika, previously worked at Messerschmitt. He designed the Gemini cockpit layout. He used principles he'd learned at Messerschmitt: standardized instrument positions, ergonomic controls, line of sight optimization. The Apollo capsule had similar German influences. NASA engineers consulted Werner von Braun's team, which included many former Luftwaffe technicians. They brought their knowledge of cockpit ergonomics from military programs. The Apollo command module had instruments in an arrangement strikingly similar to BF-109 layouts. NASA would never admit that. But photos don't lie. The instrument T formation is identical. The Space Shuttle went even further. Its cockpit displays, although computerized, show flight data in spatial positions directly corresponding to the six-pack. Speed on the left, attitude in the center, altitude on the right. The astronauts, many former fighter pilots, felt immediately at home because the layout matched their muscle memory from years in F-16 or F-15 cockpits. And those cockpits came from German designs. Today, NASA is working on Orion, the next-generation manned space capsule. Early cockpit designs released in 2019 show, you guessed it, six-pack-like arrangements on digital displays. 9 decades after Messerschmitt's LDV 435, we are still flying with German ergonomics principles. But here is the philosophical question. Did the Germans discover something truly unique, or did they simply find the optimal solution to a universal problem? First, I argue both. The arrangement is optimal because it corresponds to human anatomy and cognition. Our eyes move in specific patterns. Our arms have specific reaches. Our brains process spatial information in predictable ways. The Germans were the first to study this systematically and develop a scientifically validated solution. Other countries might have found the same answers, given enough time and research, but the Germans came first. And in technology, being first means setting the standard. Once a standard is established, it becomes self-reinforcing. Pilots train with this layout. Manufacturers build to this standard. Regulations codify it. Change becomes exponentially more difficult. Could a completely different cockpit layout be better? Maybe. But we'll never know. Because the world converged on German standards. It's an example of path dependence in technology. The choice made in the 1930s determines decisions today, and that choice was German. And what detail of this story surprised you the most? I'm curious. Many of you are pilots, engineers, aviation enthusiasts. Have you discovered connections that I haven't mentioned? Maybe you know someone who worked with German engineers in the post-war era. Perhaps you found blueprints in family archives. Share your insights in the comments. Each comment is a piece of the puzzle. In this vast history of German technological influence. In closing, the next time you see an aircraft cockpit, whether in a commercial airliner, a fighter jet, or a small private plane, remember that you're looking at German engineering. Messerschmitt, Tank, Heinkel, and thousands of unnamed German technicians solved problems the world didn't even know it had. They created standards that endured for 8 decades. They influenced every flying object that humans control. Their work was stolen, copied, renamed, but never surpassed. The six-pack flies in every cockpit today. HOTAS is universal. Ergonomic geometry is a NATO standard. German precision became the language of aviation. This isn't nostalgia. That's documented technical reality, and it deserves recognition, regardless of the complicated history from which it originates. Thanks for watching. Let's preserve this incredible technical history. Let's keep it alive for generations to come. It's a testament to human ingenuity and a reminder of the incredible feats that can be achieved, even under the most difficult circumstances. We owe it to ourselves and to future engineers to remember these stories and to learn from them.